All right. Uh, Maybe we will get started. Thank you, Krishna Kumar, for joining. And I welcome you all for the 10th problem solving session of this course, Aeroengine gas turbine cycles. So, in the week 10, you must have gone through that we have covered turboprop engines. Mostly it was turboprop engines. And the next week we will have turboshaft engines. So these two engines are something which typically in any aerospace propulsion courses if you take these two engines they don't really give much importance. They don't really how do you call uh, teach. There is no dedicated chapter they will not have, and they will not focus more on this because everyone is focusing on turbofan engines. But turboprop engines are really important, and also there is another variant of turbofan and prop, which we call it as a prop fan engine. I think that is there. There was also one numerical based on that, I guess. So uh, this class of engines are used for special purposes, like mostly they are military purposes, uh, and also for commercial purposes also they will use. For example, if they have to for example the cargo ships, and if there is any regional transport aircrafts, all those things they use this turboprop engines because it has better efficiencies, and compared to and also less fuel consumption compared to turbofan engines and turbojet engines, of course. Okay, so in this week, what we did is we studied turboprop engine, single spool turboprop to a two spool turboprop, and we briefly also discussed about turboprop engines with the intercooler and regenerator. So what I'm going to do today is I'm going to solve a problem for turboprop engines with intercooler and regenerator, which we really didn't do during the lectures. Which will give you the idea of why the intercooler is necessary, not necessary. What are the benefits of having an intercooler and regenerative cycle in a gas turbine cycle analysis? Okay. Um, so probably again, uh, so if you have any questions in this session, you can raise your doubts either in the common forum, or also you can come back again next week. We will have 2 more weeks. This is week 10, so week 11 and week 12 we will have two more interactive sessions where you can clear your doubts. And I think October 26th is your exam, and I wish you all the best for your preparations. So anyway, we will have 2 more weeks uh, apart from this week. So if you have any doubts, you can come back next week or the week 12, and you can clear your doubts. Let's get started for this week's content. So yeah, this is the turboprop engines. We all familiar. We have two additional heat exchangers, which we already also studied in the last class, right? When we solved intercooler and regenerative cycle for, I guess, two spool gear turbofan engines. So here we have turboprop engines, same intercooler and regenerator. We are introducing in a turboprop engines. And what do we what is the difference between the previous one and this one is, yeah, basically the engine is different. Otherwise, you will also note something else is different in terms of intercooler, uh, so which we will address while we are solving that part. So basically, again, in this engine, you will have uh, components like compressor, turbine, and combustion chamber, and in addition, intercooler and regenerator. But we also have additionally propeller, um, which is so our main aim is to supply as much as power to the propeller to rotate it in a to rotate it, and the propeller is the main thrust generating component here. So if you have noticed, there is no duct, across the propeller. Then it becomes a turbo fan engine. So that's the difference. So it's a like open duct kind of configuration. So uh, yeah, again from ambient, it goes to the propeller where it gets compressed, and we there is a pressure difference which causes the thrust to be generated. But the intake for the main engine is somewhat different. It is going to go from infinity to 2, but we are not going to take into account of the propeller because for various reasons. First of all, the propeller may not be stationed at front, or it may be stationed somewhere in the rear also. So um, even though the turboprop engine as it is, it looks like the air has to go through propeller first and then gets to compressor. It is not really the case. So there might be a possibility that propeller will be stationed in front of compressor, but there is also a possibility that it might be somewhere rear side, or it might be the intake of the engine would be somewhere different. Okay, so this is in general the line diagram. Not necessarily the construction needs to be like that. So let me quickly check the recordings whether it is going on. Okay. So yeah, so from infinity to 2, there is a intake component. It is not across the propeller. Please note that. And from 2 to 25, the numbering is little bit different compared to turboprop engine that we solved in the lectures. Okay. So 2 to 25 is a low pressure compressor, and then from 25 to 27 is the intercooler, and from 27 to 3 is the high pressure compressor, and 3 to 35 is regenerative heating of the compressed air, and from 35 it goes through the combustion chamber where the fuel is added and gets heated up to a higher value, and it exits the combustion chamber at T04, which will be turbine entry temperature for this cycle, and it goes to the high pressure turbine where the work is extracted from the air, and or you can say gas, and it is used to drive both high pressure compressor and also low pressure compressor. Okay, and then it goes through the power turbine or free turbine, which is going to run your propeller. Okay, and it goes through the yeah, again the exhaust gas is used for regenerative heating for the high pressure air which is entering the combustion chamber, and then once it comes out of it, it goes through the nozzle where it expands and it produces some thrust. But usually the thrust, momentum thrust which we are getting out of the nozzle would be less in this turboprop engines, whereas the thrust generated by the propeller will be very high. Okay, around like 90 to 95%, even 98% thrust will come from just the propeller. Okay, so this is the construction. In our lectures, what we solved is uh, we solved again two spool turboprop engines, but what we saw is we have only one compressor as a single component. We didn't have intercooler and regenerator. So this 25, 27, and 35, these stations were not present in that problem. Okay, so let's quickly look at the TS diagram. How will you draw the TS diagram? So there is a P infinity constant pressure line or isobaric line, and from there the air gets compressed to uh, P02, and this is due to the inlet, so diffuser action, and from P02 it gets compressed to P025, which is due to low pressure compressor, and from low pressure compressor there is a intercooling session, so it goes so the temperature drops a bit, and that is what you see at uh, from 205 to 207, and you also see a small drop in the pressure because intercooler and regenerator comes with some pressure losses. So during this process there is some Q you are extracting, uh, uh, but it is actually going to the ambient, so that is the difference. So so since this is an intercooler, so it has to get cooled down, so air which entered the compressor has to get cooled down before it is fed into the high pressure compressor. But what is going to cool it down is actually the here we are going to consider it as the atmospheric air. Okay, so just the heat exchanger goes out, and then the atmospheric air which will be at T infinity will flow through this heat exchanger, and it reduces your uh, what do you call the temperature of the low pressure compressor, temperature of the gases or air which is exiting the low pressure compressor. And from 27 you have high pressure compressor to 3, and from 3 you have uh, regenerative heating till 3.5. uh, so currently we don't know where exactly it is. So after that you have combustion chamber where you reach the turbine entry temperature of T04, and from 4 to 4.5 you have high pressure turbine, and from 4.5 to 5 you have power turbine, and from power turbine you have regenerative uh, cooling for the exhaust gas and regenerative heating for the incoming gas. So from 5 to 7 is the regenerative cooling, and uh, corresponding heating of the exhaust the incoming gas would be from 3 to 3.5, which is Q regeneration. And the remaining from 3.35 to 435 to 4 is what uh, is the amount of heat given by uh, is given from the fuel, okay, because of combustion. And from 7 to 9 you have the nozzle expansion. So this is your entire TS diagram. I'm sure you guys must be familiar with this. And moving forward, this is our problem to solve today. We again have the same regional passenger aircraft, which is going to cruise at an altitude of ambient pressure 38 kilopascal and temperature to be minus 30 degrees Celsius. So this problem is same as what we solved in the lectures, but only thing is we have added intercooler and regenerator, and we are going to see what is the benefits it is going to give uh, in adding intercooler and regenerator in a turboprop engines. Okay, and the core mass flow rate here is 2 kgs per second, and the turboprop engine cruises at a velocity of 320 kilometer per hour, and the design power split between low pressure turbine and the engine nozzle is 0.95. So I'm sure you must have known this design power split. Uh, this we have discussed in detail during the lectures, but anyway, we will again go through those steps again. And the ambient pressure and temperatures are given. The low pressure compressor pressure ratio is 2, and high pressure compressor pressure ratio is 3.5. In in your lectures, what you must have noticed is we have only one compressor, and that compressor's pressure ratio is 6.3. Here we have divided it into two. However, the overall pressure ratio is still 6.3. So 2 times 3.15 is 6.3. So and turbine inlet temperature is 1212 Kelvin. Intake pressure recovery is 0.98, same as in the lectures, and total pressure loss is 2%. So intercooler effectiveness and regenerative effectiveness and pressure losses are given, and fuel heating values and core engine mass flow rate, of course, we know. And these are the given properties, and also the efficiencies and losses is also given. So now we are going to use these parameters, and we are going to find out performance parameters like power, thrust, and equivalent shaft horsepower and equivalent uh, fuel consumption. So without intercooler and regenerator, what we saw is we got a net thrust of 4.37 kilonewtons, which corresponds to 603 horsepower, and we have some TSFC and ESFC, and the overall efficiency was around 20%. Okay, now we have added intercooler and regenerator. Let's see what happens in our present engine. Okay, so so the way we are going to solve is going to remain same. We need to solve inlet and the low pressure compressor, and pressure and temperature from the low pressure compressor has to be used for an intercooler. Now, as I said, the intercoolers, the cold fluid which is going to cool the uh, gases coming from the low pressure compressor is going to be ambient pressure, and from there we can find exit pressure and temperature, because we know the effectiveness of intercooler. Exit pressure and temperature of intercooler we know, and based on the HP compressor pressure ratios we can find pressure and temperature at the exit, and then it goes to the regenerator. But for regenerator you also need to know the exhaust gas conditions, and so we may need to do some iterations over here. So once we know pressure and temperature from the regenerator, we can solve a mass conservation equation for combustor to find the fuel air ratio, and also pressure loss we know across the combustor. and from there you can find the you can solve HP turbine work balance to get pressure and temperature at the exit. And going forward, you have low pressure turbine, which is also called as power turbine here. And the power turbine is used to run the propeller. And across that you can find the pressure and temperature at the exit of the turbine, which is going to reheat the uh, incoming gas from the high pressure compressor exhaust. So from regenerator, this exhaust gas goes through the nozzle and generates velocity V9, which is going to generate thrust. Okay. So this is the architecture how we are going to solve this problem. And first, initially we have inlet. So inlet, we need to know the flight Mach number. So if we use 88, so 320 kilometer per hour is nothing but 88.88 meters per second. So there is a meters per second missing, which I will correct. And the flight Mach number here is going to be 0.28. Now the intake process, there is no change as such in the intake process compared to compared to the lectures. There's no change. We have taken the conditions to be same. So we would expect the pressure uh, to be pressure at the exit of the inlet to be same as we got during the lectures. Okay, so which is indeed true. And we got the pressure and temperature at the exit of the inlet to be 39.32 kilopascal and temperature to be 246.81 Kelvin. Okay. um, yeah, so this is about inlet. So after inlet you have low pressure compressor. So here is where things will change, because in the lectures we had only one compressor and the compressor pressure ratio was 6.3. Now we are going to do it in two-step process. So initially our compressor pressure ratio would be 2. So directly comparing the temperature and pressure of in the right hand side may not be the wise choice. Maybe after high pressure compressor, we can compare and see how the pressure and temperatures are different compared to whatever we got during the lectures. Now, yeah, so the low pressure compressor has a pressure ratio of 2. So if you multiply it, you will end up having pressure at the exit of the low pressure compressor to be 78.64 kilopascal. Now that you know the pressure, you can also find the temperature. The temperature here, what they have given is they have already given the polytropic efficiency. So from the polytropic efficiency, you can directly find the temperature ratio. And from the temperature ratio, you can actually find the temperature at the exit of the low pressure compressor. So that's what we are going to do here. And the formula wise, both are same. There is no much of a difference. Only thing is the pressure ratio would be different compared to whatever we solved. So if you substitute these numbers over here, T025 by T02 would be 1.2359, and T025 you can find out to be 312.43 Kelvin. And yeah, of course this will not directly match because we haven't reached 6.3 multitudes of pressure. So this is just first low pressure compressor. So the next component that we have is intercooler, and in the intercooler what we have is the low temperature ambient uh, air is going to enter and cool your relatively high temperature uh, exhaust from the low pressure compressor. And we already have intercooler effectiveness, and we also know how we get intercooler effectiveness, how this formula comes. So I'm not going to go into much detail. As I said, this is nothing but actual heat transfer by maximum possible heat transfer. And if you work out the formula, you will end up having the intercooler effectiveness formula to be T025 minus T027 divided by T025 minus T0 infinity, which is the cold air which is going to enter. Now, if you substitute these numbers, what you will get is you will have temperature to be lower for around 253.37 Kelvin. So the temperature with which the gas entered the intercooler was 312 Kelvin. From there, it has reduced to 353.37 Kelvin. Now, intercooler also, in the intercooler, you also have pressure loss. So that pressure loss was 2% of the inlet pressure. So if you do that calculation, you will end up having exit pressure to be 77.07 kilopascal. And the next component that we have is this cold air, or the intercooled air at pressure of 7707 kilopascal and temperature of 253.37 Kelvin is going to enter the high pressure compressor, where the pressure ratio is going to be 3.15. And at the end of this, you will have proper comparison with the lectures, whatever with the numbers that we got in the lectures. Okay, now the pressure ratio is 3.15. So it's going to be 3.15 times 77.07 kilopascal. That would be the exit of the high pressure compressor. And that was around 242.77 kilopascal, which is slightly less than the, in the lectures when we got 247.74 kilopascal. And we can actually relate that because the we have taken some heat out of the system, right? So which is nothing but some energy has been taken out, and because of that, the amount of pressure rise that you get in the compressor would be relatively small compared to uh, what we got in the lectures when we have a single unit as a compressor, right? And similarly, you will also end up having a lower temperature because it is intercooled. It's straightforward. So if you substitute these numbers, you will end up having temperature to be 374.32 Kelvin, which is as expected because our air has been intercooled in between. So it has to, after compression, it has to stay at a lower pressure and temperature compared to the case where the intercooling haven't happened. All right. So this is till the compressor, there is no problem. Till compressor, everything is good. Now, from compressor to combustion chamber, there is an intermediate component called regenerator. Now, in the regenerator, what happens is some amount of heat is being already transferred to the incoming gas. So it gets heated to a certain high value. And from that high value, we are adding fuel to do combustion, and then we are going to reach the turbine entry temperature. So this without calculating intercooler, you cannot go to the combustion chamber. So in the regenerator, sorry, without calculating the regenerator station properties, we cannot go to the combustion chamber. So in the regenerator, again, it's an heat exchanger. So it has its effectiveness. We can use that. So before going into that, let's see how the pressure has changed. So we have 2% loss in the pressure. So it entered at 242.77 kilopascal. So 2% loss would be something like 237.91 kilopascal. So this is the pressure with which the incoming hot gas from the high pressure compressor is going to exit the regenerator. Now we also need to find T035. That is the temperature with which it exists, because that is necessary to find the combustion chamber. So how do we do that? So we have effectiveness, and effectiveness of a regenerator is nothing but T035 minus T03 divided by T05 minus T03, which is T in of both hot and cold stream. So here the hot stream is exhaust from the power turbine. So the power turbine here is station number 5, and inlet of this HPC, sorry, inlet of this regenerator is station 3. So that's what you see here, T05 minus T03. Again, the numerator is nothing but actual heat transfer divided by the maximum possible heat transfer. And if so, if you can, if you rearrange this formula, you will end up having T035 to be this formula, T03 plus effectiveness of regenerator times T05 minus T03. But the problem is we don't know T05 because we are still in the regenerator. We haven't reached power turbine. So until unless we know T05, we won't be able to find T035. So that is one problem that we are facing now. So then what can we do? So then you can go ahead and find what is T05. So we can take a reverse approach. So what would be T05? T05 would be coming out of the power turbine. So let's say if you do a energy balance for the power turbine. So the ideal per unit mass available at station 4.5. So since it's a power turbine, we exactly don't know what is the amount of energy required for the propeller, and what we know is power split. So the amount of power split for the power turbine is around 0.95, and the remaining power is only used in the nozzle. So at 4.5, you have some ideal amount of power available. In that, 95% is going to be used by the power turbine. So that is what we are going to do here currently. So the ideal amount of power. So first we need to find how much is the ideal amount of power. Then we can find what is the amount of power turbine this propeller is going to do. I mean, what is the amount of power turbine? What is the amount of power from the power turbine? In the other way, what is the amount of power generated by the propeller is going to come from this ideal power at the exit of HPT. Okay, so the power would be something like m dot c into 1 plus f, which is the total mass flow rate in the power turbine, times H0 4.5, which is the exit of the HPT, to if you expand it, isentropically, then it will go through H9i. Okay, so that you can write it in this formula. So this is all we know. If it's an isentropic process, we can write this as P9 by P0 4.5 gamma minus 1 by gamma. Okay, it's from isentropic what do you call, so basic thermodynamics, so you can work it out. So the power delivered to the LPT can be calculated by power split factor. So this is the ideal amount of power required, so our ideal amount of power available at the HPT exit. Okay, from exit I have some high pressure and temperature gases. From that I can get the ideal amount of power that I can extract is this much. Okay, and this engine is designed for extracting alpha amount of power from that HPC exit. Okay, so that's why we multiply this whole thing with alpha, and since the low pressure turbine has some efficiency, it also includes that term. So the power delivered to the low pressure turbine will be equal to m dot c into 1 plus f into alpha into eta LPT times this portion H0 4.5 times 1 minus this thing. Okay, so this is going to be equal to, this whole thing is going to be equal to whatever the pressure and temperature loss across the power turbine. So what would that be? Or you can say enthalpy lost across the power turbine. So that would be H0 4.5 minus H05. So finally we need to find H05. You can write H enthalpy in terms of Cp and T. So if you do this calculation and then rearrange this whole thing, our interest is to get T05. So T05 would be equal to T0 4.5 minus this whole thing. So what we know is P9, we can assume it to be expanded to the atmosphere, and P0 4.5, T0 4.5 we need to know, because we don't know P0 4.5 and T0 4.5 in order to find T05. So those are the two, again, new unknowns that is coming from. So we need to find what is T0 4.5 and P0 4.5. Then only we can find T05, and then only we can find the exit of the regenerator. Okay, so please understand how the thought process is going through. So now T0 4.5 and P0 4.5 can be found only if you solve the power or energy balance for the high pressure turbine. In the high pressure turbine, the work generated by the high pressure turbine is actually used to drive the high pressure compressor and the low pressure compressor. So this is the energy balance for this high pressure turbine. So if you substitute the appropriate expressions for it, you can notice that for high pressure turbine you have this 1 plus f, which is obvious because we added in the combustion chamber we are going to add some fuel. And for high pressure compressor, it is operating at T03 minus T027 between these two stations, and for low pressure compressor T025 and T02. So you can notice that these two are not, so T025 and T027 are not same temperatures, which is something different. And yeah, so that is if you drop the m dot core and if you rearrange this, you will end up having T04.5 expression. We still don't know P04.5, we have to find that. And also in this expression, what we don't know is we don't know F, right? So we haven't gone after high pressure compressor. So we are just finding the unknowns, new unknowns, how to solve this relation. So we don't know F again. So what is F? That is one thing. So to know the F, we need to, uh, look at the combustion chamber. So before getting into the combustion chamber, let's try to find out. So another unknown is P04.5, which is also associated with the high pressure turbine. Uh, let's use the isentropic relationship for the efficiency to find the pressure at the exit of the high pressure turbine. So that would be something like this. So we already know. So we have used this pressure. We have used this equation in order to find pressure at the exit of the turbines in previous problems. So we now here this equation we are going to use it in an iterative manner additionally. So that is the difference. So again here what we know is what we don't know is again what is P04. So the another unknown. So now the unknown is F and P04. If we know this F and P04, we can find P04.5 and T04.5. And if you know those two, you can find T05. And if you know T05, you can find uh, T035. Okay, so all this is for because of this regenerator present in between HPC and combustion chamber. So as I said, we need to know F and P04, that is from the combustor. From combustor, we can easily find P04 because across the regenerator, we already found the pressure P035. And in the combustion chamber, again, there's going to be pressure loss of 2%. So we can directly find P04 to be 233.15 kilopascal. Now, one unknown is solved. So the another is F. We need to find the fuel air ratio. So for that, we will do energy balance, which we all know. And if you rearrange this equation at the end, you will end up having this energy balance to be uh, in terms of fuel air ratio to be CPH T04 minus CPC T035 eta B QR minus CPH T04. Now T04 is turbine entry temperature, which is given in the question. QR and eta B, CPC, CPHs are given. Only thing is T035. So that is where we started. So we don't know T035, and then we went to power turbine, and then we went to HPT, then we came to combustion chamber. Again, what we don't know is again T035. So it has actually made a loop. So we have 5 equations till now we have discovered, which we couldn't solve, and we had 5 unknowns. One is T035, T05, T04.5, P04.5, and F. Okay, and how are we going to solve? Is initially you this is one way to solve. Initially you guess F, and once you guess F, you use the HPT work equation. From there you can find T04.5, and from T04.5 you also find P04.5, and once you know P04.5 you can find T05, and you can find T035, and again you can find F, and then you can, with this new F, again do these iterations until you find F to be same. Okay, so once you have this F, so I've just wrote a simple MATLAB code to do this in iteration. You can use this, or you can even do it in hand calculation. Within 2 iterations it's going to converge. Okay, so if you do this iteration, at the end you will end up having these numbers. So the fuel air ratio would be 0.0159, and the T035 would be 762.85 Kelvin. Okay, so uh, let's go back and see what happened. So the T035 is nothing but a regenerative temperature. It's the temperature of the gases from the high pressure compressor, which also receive regenerative heat from the exhaust. So from I think around 300 Kelvin or so, I guess. What was HPC exit? So if you go back some slides, regenerator. So if you look at it, the T03 is 374.32 Kelvin, And in the regenerator, what happened? There is a substantial amount of increase in temperature from T0, some 373 point, so some 374 Kelvin, from 374 Kelvin. How much was the increase? Around 762.85. Okay, from 374 to 762, around like 300 Kelvin increase that you can observe, 300 to 400 Kelvin increase in the regenerator, and then it goes to the combustion chamber. So in the combustor, what you have is 762.85 Kelvin uh, hot gas, relatively hot compared to high pressure compressor, but combustor it is going to go to high temperature of 1212 Kelvin, 1212 Kelvin. And the pressure from the exit of the regenerator is 237.91 kilopascal. Pressure loss we already found it to be 233.15 kilopascal. This is less than whatever we got in the lectures, because HPC exit was also lower, regenerator also lost some pressure, so we should expect the pressure to be lower than what we saw in the lectures. And now the energy balance, if you do, we already found the fuel air ratio from the MATLAB loop also, and the fuel air ratio was around 0.0158. Okay, and compared to the uh, lectures, for the same compressor pressure ratios and same uh, inlet conditions and things like that, for the same operating conditions, your fuel air ratio is substantially lower compared to you know engine without intercooler and regenerator. You can see our fuel air ratio is around 0.0159. You can even say 0.016. And here in the lectures that we saw, we have 0.023. Okay, let's see how much of a difference that it makes in terms of efficiency. Now the next component is HP turbine, and again we solved P04.5 and T04.5. I don't need to go through it again. So the T04.5 that we got is 1050.32 Kelvin, and whereas the temperatures are little higher, because if you think about it, the HP turbine is running high pressure compressor and low pressure compressor, and the overall pressure across which the amount of work the HP turbine needs to give is same, which is 6.3, right, in both these cases. But the only thing is, because of intercooler, some of the energy is lost in the intercooler. So the amount of work required to compress that low energy air is going to be lesser, and because of that, the amount of work spent or amount of work needs to be extracted by the HP turbine is lesser. And if the amount of work needs to be extracted from the HP turbine is lesser, the exit temperature and pressure is going to be little higher. So that's what you see here. T04.5 is higher than T04.5 that we got in the lectures, which was around 1027. Here we are getting some 25 Kelvin rise. Okay, and the pressure again, as expected, it should be higher than P04.5, which is what we expect. So let's see what happens. As expected, the pressure is also, basically we no need to extract more energy out of HP turbine. If we no need to extract more energy out of HP turbine, the exit pressure and temperatures are going to be higher, right? So that is what is happening here. So P04.5 is around 117.17 kilopascal. All right. Now LP turbine, or you can say power turbine, which is going to run the propeller. So for this, so now that we know T04.5, we can actually find the T05. T05 is going to be 831.42 Kelvin. Now that we have known T05, we can actually find the power of the LP turbine. How much is the amount of power that that can be extracted from the LP turbine? This will be something like 512.36 kilowatt, and this is also higher. That is something you should know, because the inlet pressure and temperatures for this LP turbine is higher. So and naturally the amount of available energy at the exit of the HP turbine is higher, and since those are higher and the power split factor hasn't changed, we have power at the low pressure turbine can extract more power, and that is what you see here. So around 512.36 kilowatt is the amount we can extract. However, in the lectures we were able to see only 478.23 kilopascal. Okay, so all these are pointing to a direction that the efficiencies would be higher. Let's see what is the amount of increase in efficiency that we are going to see. So we also need to find pressure at the exit of the LP turbine. So we can use the isentropic efficiency relationship, and we can find the pressure at the exit of the LP turbine, which will be around 40.53 kilopascal. Okay, and this is not that much of a difference because uh, we have extracted enormous amount of power, and so the pressure has to come lower, and at this point it is closer to whatever we got from the previous results. All right. So yeah, and one more thing is, from the exit of the low power turbine, the exhaust gas goes to the regenerator. So this is an additional component that you need to solve. So again, the exit pressure would be a 2% loss in the pressure, and if you calculate that, you will end up having the pressure to be 39.72 kilopascal, which is less than 40.53 kilopascal. And once then also you can do energy balance to find the temperature at the exit, because you remember substantially there was an increase in temperature from 374 to around 762 Kelvin in the incoming air. So there's going to be substantial reduction in temperature of the regenerative air. So if you include that part, it's going to be the temperature at the exit of this regenerator is going to be 498.11 Kelvin. So this energy, the energy of the exhaust gas now after the regenerator is going to be very less compared to what we got in the lecture. Okay, because the energy which was going into the nozzle is higher in the lectures because we didn't have a regenerator, and you can clearly see from the temperatures and pressure. Here the pressure and temperatures are, that is 39.72 kilopascal and 498.11 Kelvin. Whereas in the lectures, if you remember, it was, so you can note here, the turbine power turbine exit temperatures is very high. It was not 490, it was 824.46 Kelvin. So the energy that we are leaving for the nozzle is very less at this point, whereas in the lectures we are leaving a lot of energy to the nozzle. So let's see what happens in the nozzle. So the next component is nozzle, and first, as usual, we need to find the choking condition. Using the choking condition, you can find the critical pressure to be 21.717 kilopascal, and that leads to around that is less than 38 kilopascal, right? So the nozzle is unchocked, right? And hence the exit pressure would be same as 38 kilopascal. I think there is some sign mistake here. It should be less than sign. Okay. So now the nozzle is chocked. No, sorry, nozzle is unchocked in both the cases. That is what we saw in both the cases. But the exit velocity is going to be different because our energy at the inlet of the nozzle is lesser. So let's see what happens. You can find the exit velocity to be 110.84 meters per second, whereas in the lectures we got 165.93 meters per second. So there is some, you know, how do you put it? So there is going to be some balance because of intercooler and regenerator. You might have generated a lot of power for the propeller. However, you must have lost the power in terms of core stream. Okay, that is what you are seeing here. Now, we should also find the temperature at the exit of the nozzle in order to find the Mach number at the nozzle exit. So that you can find out if it is ideal expansion, you will end up having a temperature at the exit of the nozzle to be 492.667 Kelvin. However, nozzle has some efficiency of I guess around uh, 98%. So if you do that calculation, you will end up having temperature at the exit of the nozzle to be 492.78 kilopascal. So that's going to be a little higher than the isentropic expansion. And that is, very less compared to what we got in the lectures, which was 812.5 Kelvin. So you can find the Mach number of the gases at the nozzle exit, that will be also reduced to 0.254. Okay, which makes sense because the velocity also reduced from 165 to it reduced to 110 meters per second. All right, so now the important things, we need to find out what is the performance parameters for this turboprop engines. The first performance parameter that we have here is propeller thrust, and the propeller thrust is going to be uh, we are going to find using the propeller efficiency, because finding the propeller thrust from the propeller is going to be a little bit difficult, um, and we have also seen multiple ways to find out. Instead, uh, so people have done these extensive studies, and they have came up with a quantification number called this propeller efficiency. So that is going to help us in finding the propeller thrust. So here you can see this is the total power. P LPT is the total power at the exit of the LP turbine, and since these are connected through shafts, you have mechanical efficiency in the LP turbine, and also there is additionally gearbox will be present, so that efficiency of gearbox. And then you have, so this eta GB, eta M LPT and P LPT is the total pressure available, total power available for the propeller. So that is the propeller. And the propeller efficiency is nothing but the thrust generated by the propeller divided by the power given to the propeller. Okay, that is the efficiency. So you can understand this. Thrust generated multiplied by V infinity is the amount of power generated by the propeller divided by the total amount of power given to the propeller. Okay, total amount of power given to the propeller would be simply eta GB, eta M LPT, P LPT. Okay, so if you do the math, you will end up having this relation, and from here you can find the thrust generated by the propeller. So you can substitute these numbers. All the efficiencies are same. Only thing is the power produced by the LP turbine is higher here. So we end up having higher thrust here, which is around 4.45 kilonewton. However, in the lectures we saw only 4.21 kilonewton. Now the core thrust is going to be lesser compared to what we saw in the lectures because our velocities are lower, so which is expected. And yeah, so we have very substantial reduction in the core thrust. So from 161 we have reduced to 47, which is one third of the more than one third of the reduction in core thrust. But at the end of the day, we are interested in total thrust. Also, the propeller thrust is what is important, because around like 98 to 99% of the thrust is coming from the propeller. So if you substitute these numbers, you will end up having 4.497 kilonewton, which is around 4.5 kilonewton. However, we got only 4.37 kilonewton. So we are generating more thrust because of this intercooling and regenerator. Okay. Now looking at the power, what is the total propeller power? I mean, it is the power given to the propeller. So that will be, as I said, it will be simply eta GB, eta M LPT times power generated by the LPT. So that is around 481.87 kilowatt. And now the power produced by the core engine is around 4.22 kilowatt. So the equivalent shaft horsepower you can find out. That is nothing but the shaft power, which is P propeller. So which is P propeller plus this is a shaft power that has nothing to do with the propeller. So that's why there is no propeller efficiency coming in. What is the amount of shaft power that you have generated? So the equivalent shaft horsepower is nothing but the amount of shaft power generated in terms of horsepower is what they are asking. So since we also generated power using the nozzle, during the core thrust because of the nozzle, so we are also including that part over here. And If you substitute these numbers, you will end up having 652 horsepower compared to what we got was 603 horsepower. So we got additional some 40 to 50 horsepower. Okay. Now, yeah, important parameter TSFC. Whole point of doing this turboprop engine. How much difference is the TSFC? We can find out. So if you substitute these numbers, we will end up having, this decrease in TSFC from 10.52 to 7.07 is a good amount actually. So this will be, in the long run, it's going to be economically beneficial. Okay. Similarly, you can also find equivalent specific fuel consumption, and that is going to be in terms of power. Okay, so this was in terms of thrust. That's why thrust specific fuel consumption. Here it is going to be, we are going to normalize with equivalent shaft horsepower. So again, if you substitute these numbers, you will end up having reduction in specific fuel consumption from 0.605 to 0.387. All right. So finally, we also need to find efficiencies. So the thermal efficiency here is quantified from equivalent shaft power, equivalent shaft power divided by m dot f into qr, which is nothing but the amount of energy that we gave in terms of fuel. So if you substitute these numbers, you will end up having 36.46%. So very huge increase in thermal efficiency from 23.3%. Okay. And the propulsive efficiency that we can calculate it based on the total power generated uh, from the entire engine, which is T total, which is T propeller plus the T core times the V infinity, divided by the total amount of shaft power that was given. Okay, ESV. So if you substitute these numbers, you will end up having a propulsive efficiency of 82.07%, which is slightly lower than what we got in the lectures. Now, however, the efficiency in because we have rise in thermal efficiency, that is going to outweigh the overall efficiency, which we can see for ourselves. It was around 29.92%, whereas in lectures we got 20.1%. So you might feel that how come an intercooler and regenerator can give a very high increase in efficiencies. So intercooler and regenerator are designed to improve the efficiency, but an increase in efficiency of this much may not feel unphysical, because so you should also note what are the simplifying assumptions that we made for the intercooler. If you look at it, there was an assumption that the ambient air is used for cooling. So ideally, it may not be the case. The air may not be at ambient temperature and pressure. It might be at a different temperature and pressure because of the position of the propeller that is going to be there. And also the effectiveness of the intercooler for such a system might be less, but we took the same effectiveness, but we might have taken a very high effectiveness of that intercooler, and also same regenerator. Okay, so those intercooler and regenerator, the effectiveness and the pressure loss parameters is kept to be same as in two spool gear turbofan that we saw um, last week. So it may not be same here also, because the two spool gear turbofan is very efficient because it is running at a high speed around Mach 0.8 and all. So at that time you might have good effectiveness, but it may not be that much effective when you have when you are in a turboprop engine. So you should also note that those changes. So these additional optimistic input that we took might have led to this higher efficiencies. So usually what people observe is their target is to get a very at least a 4% increase in intercooler and regenerator. That is what people usually see. So in reality, from 23.3% you can go up to 27 or 28%, while we got here to be 36.46%. Okay, so you can do this as your homework, or whenever you are free, you can do this exercise of varying the effectiveness of the intercooler and regenerator, and also the pressure losses, and see where it lies. Okay, So I haven't personally came across any turboprop engines with intercooler and regenerator. So if I come across, I will share it with you. Uh, all right, but I think there are few engines, so there should be some engines in order to improve the effectiveness and efficiency. Sorry, in order to improve the efficiency and reduce the specific fuel consumption. All right. Overall, the picture is when we added intercooler, you can see that the net thrust has increased around 2.9%, 3% increase in thrust we got, and the equivalent shaft horsepower is around 8% increase in this shaft horsepower we got. TSFC, there is a reduction of 30% reduction, which is um, it might be unphysical, but you can expect a reduction of at least 10%. Okay, and also 36% reduction of ESFC you got, and better efficiencies that we got when we added intercooler and regenerator. All right. So yeah, basically that is the overall idea of adding an intercooler and regenerators to improve the efficiencies basically. So here we got in terms of thrust we didn't get that much improvement. Sometimes it might be detrimental also. Uh, let's be frank. So the net thrust might reduce a bit also because of this intercooler and regenerator. Um, but to a certain extent it increases, but after that it will drop. So but the whole point of adding an intercooler and regenerator is to improve the efficiency and reduce the fuel consumption, which we can evidently see from this numerical. Okay, so um, that is something that I wanted to show today. And if you have any doubts in this numerical, you feel free to come back next week and ask those questions, or you can use the common forum to ask this question. And the next week we are going to solve a turbo shaft engine. That would be our week 11. And week 12 we might most probably we may not solve any engines, but we might most probably do a revision of whatever we learned in this uh, course, so which should be helpful for you for preparing your exams, which is going to be on October 26th, I guess. All right. I thank everyone for watching this. Whoever is going to watch this video as soon as I post in YouTube, and I also thank Krishna Kumar for joining. So if you have any doubt, you can ask. If you don't have any doubt, we can meet again next week. Thank you very much. Okay. 21.17 is really less than 38 kiloparscal, so it's a null chop. All right.